All right, and for our final vignette talk of the pre-lunch era, we are going to hear from a brand new KIPAC postdoc, Jaeyeon Kim.
Hello, everyone. My name is Jaeyeon Kim. Today, I will be giving a very brief introduction of our PHANGS survey data. PHANGS is short for physics at high angular resolution in nearby galaxies. And we have constructed a data set that is high resolution and multi-wavelength of the nearby galaxies with an aim of resolving nearby galaxies into individual star-forming units. During my PhD, I have extensively used this data set to constrain the timescales associated with different phases of star formation processes, which I will briefly also discuss in this talk. So in PHANGS, we focus on normal star-forming galaxies. In such systems, we can naively say that gas flows into these galaxies, turns molecular, and forms stars. Much of star formation and galaxy evolution occurs along this sequence, where the x-axis is the molecular gas surface density, and the y-axis is the star formation rate surface density. However, in PHANGS, we wanted to focus on what is behind and beneath this global trend. We wanted to study the engine that is driving the galaxy growth, which is the violent feedback cycle between gas and young stars. To be more specific, these star-forming regions first start from diffuse atomic gas phase, and then they form bound molecular clouds, which collapses and forms stars. These newly formed stars inject energy and momentum into the surrounding gas, creating H2 regions, and then finally only leaving young stars to be observed without associated cold molecular gas. So these kind of processes of star formation and feedback takes place on a scale that is much below the scales of the whole galaxy, and these regions undergoing evolution from gas to stars have sizes about 10 to 100 parsecs and observed as molecular clouds, H2 regions, and stellar clusters and associations throughout the whole galaxy disk. One of the major questions that remains unanswered in this field is actually the detailed characterization of the physical processes that are responsible for the regulating the matter of cycle between gas and young stars, and how these processes depend on different environments. So in order to solve this kind of questions, we need first high resolution observations and also resolve these galaxies into individual star forming units. And more to that, we also need a multi-wavelength approach because these kind of star-forming processes are only observed using different observables. For example, here, the initial molecular gas phase is only observed using CO emission, mostly from ALMA. And then deeply embedded star-forming phase takes place, which is only observed using infrared emission, mostly from previously Spitzer, and then now JWST. And then the star-forming region reveals itself from the parental cloud, making it visible to be in H-alpha emission, which can be observed using HST and MUSE, and as well as in ground-based telescopes. One of the biggest limitations that we had in obtaining this kind of high-resolution observations for numerous galaxies is the lack of high-resolution observations of CO and infrared emissions. However, during recent decades, there has been a huge advancement in obtaining high-resolution CO observations thanks to PHANGS, thanks to ALMA. So PHANGS has conducted a dedicated survey of targeting 90 molecular gas-rich galaxies in order to obtain high-resolution molecular gas observations. And for the same set of galaxies, we also have H-alpha observations using ground-based telescopes. For a subset of these galaxies, we also have observations from HST and UV satellites. And also for subset of them, we have MUSE observations, and 19 of them also have JWST observations from cycle 1. And this cycle 2 started actually just today, and we were able to make first observations of one galaxy, but now we're going to have more galaxies, in total of 55 more galaxies. So all of these observations can be used to trace distinct phases of the star formation processes. So now this is an example of a CO observation map that we have, and you can see that this high resolution CO map has sharpened our view of cold gas throughout the whole disk of the galaxy. These CO observations reveal that cold gas has clumpy structures at size scales of 100 parsecs, which roughly corresponds to the size of the giant molecular clouds. And this is an image of all the galaxies in our sample in CO observations. And these all data are publicly available. And so I have to talk about what we have learned from all of these observations. First, when we had these CO observations, we of course started by measuring the conditions of these molecular clouds. We find that there is a wide range of conditions of these clouds, as shown here in the case of the molecular gas surface density and line width. They have a very wide range, and they seem to depend on the location where they are within the galaxy, as indicated by the color of the data points, which is the galactocentric radius. So why is it? What is happening here? One plausible answer might be that these small scale GMCs, molecular clouds, still care about where they are within the galaxy. This is indicated here on this plot here, where the y-axis is the internal turbulence pressure of these molecular clouds, and the x-axis is the pressure that is required to support the weight of the disk. And there's a tight correlation between these two pressures, meaning that GMC properties still care where they are within the galaxy because they still reflect the overall disk structure. And also using high resolution observations of CO and H alpha observations during my PhD, I was interested in deriving the timescales of this giant molecular cloud evolution. As you can see on this figure here, high resolution observations are showing that CO and H alpha observations are showing spatial offset on small scale. This kind of spatial offset indicates that, let me start over. So this kind of spatial offset is visible here on this figure here on small scale. However, this CO and H alpha observation seems to trace one and another on a larger scale, defining the well-known star formation relation. So during my PhD, I have used this kind of spatial offsets on small scale in order to derive the time scales of GMC evolution. And we find that this kind of GMC lifetime giant molecular clouds are very transient objects. They seem to survive about 10 to 30 mega year, with showing a dependence on the host galaxy mass. And stellar feedback is very violent, dispersing the molecular clouds within a few mega year. And this kind of feedback terminates a star formation right after, resulting in low star formation efficiencies of these clouds. So here, as I mentioned earlier, the other limitation was the lack of high resolution observations in mid-infrared. However, now JWST is revolutionizing this view. Compared to Spitzer, JWST has like 8 times better sensitivity and resolution, and you can see the significant differences here already in this figure here. So PHANGS, we have observed 19 galaxies at wavelengths from 2 to 21 microns, and these kind of images have physical resolutions of 10 to 50 parsecs. And now I'm just going to show pretty images. This is NGC 7496. Here I see 5332, and this figure here is actually CO map from ALMA, and this was the best map that we had so far of this galaxy. However, now with JWST, we are seeing so much more structure at a very higher resolution, which is really nice. And this is NGC 1365, and this is 628, which is one of the closest galaxies that we have in our sample. So early this year, using this initial 4 observations, PHANGS has published 21 letters using these observations. So the key science insights from this work has been filaments and bubbles are everywhere, as you have seen in these previous images. And then it seems like that small dust grains that JWST traces seems to be like one of the most accessible high resolution observations of the gas in the interstellar medium. And it seems to trace both atomic and molecular gas phase. And also using the longest wavelength at 21 microns, which is the most sensitive to the embedded stellar populations, we find a lot of embedded star formation in stellar populations. So using this wavelength of 21 microns, I was interested in answering the question, how long this deeply embedded phase of star formation takes place. Using the same statistical method, we find that this phase, early phase of star formation, takes place about 2 to 3 mega-year, up to 2 to 3 mega-year in the case of NGC 628. This short star forming phase actually implies that it is most likely the pre-supernova feedback, such as stellar winds and photoionization, that are responsible for the feedback processes and termination of further star formation. And now this is a summary. Resolving galaxies into individual star forming units has been a big advance. And then using these observations, we find a close link between small scale molecular cloud evolution and large scale host galaxy environmental properties. And using these observations, we also found that stellar feedback is very strong and it quickly reshapes the interstellar medium, dispersing the molecular cloud. JWST has been amazing so far, and there will be a lot more science-ready images to come in the future. And particular interest of mine, it will be using JWST observations as a tracer for atomic gas, with an aim of providing a more complete picture of star formation, including the phase where atomic gas is transitioned into molecular gas phase. And I'm happy to take questions now.
Thank you for that beautiful talk. Exciting data and exciting discoveries. All right, we have a question here.
Thank you for such a wonderful talk and all the beautiful pictures. I wonder if you can say a little bit about the galaxy sample selection and how that impacts the science. And then looking forward, what kind of galaxy sample that you are most excited about for further science into the future?
Okay, so this is kind of summarizes our sample here. We are very close, redshift 0.0, with distances less than 25 megaparsecs. And we try to focus on galaxies that is not so edge on because we want to see the disk of the galaxies. So the inclination cutoff is about at 75 degrees. And because we are using ALMA, it has to be ALMA accessible. So actually, basically, we are almost observing all the galaxies that are ALMA accessible and that are close nearby. Yeah, and the galaxy that I'm interested in is actually towards more metal poor galaxies because they did not have enough CO emission like you saw in the IC 5332, and I couldn't do any science with it. But now with JWST, we're seeing so much gas that was not detected in CO emission, and I think there is a bit more science to it in terms of pre-supernova feedback. They might have less stellar feedback, but stronger photoionization. I want to see if this is really true, and this is what we're seeing.
These images are just so beautiful. So congrats on this exciting work. Could you say more about what we learned, the distribution of those bubble sizes within a galaxy and from galaxy to galaxy?
So we did in the letter that we published this early year, Elizabeth Watkins, actually, she studied the bubbles and size distributions in the case of 628. And then like there is a distribution, but it seems to be cut off at the size of the disk scale height. So it means that like some kind of galactic fountains is happening there. And yep, I think that's the case for now.
Yeah, let me just echo how spectacular these images are there. Wonderful. I have a feeling they ought to also be telling us something about the dynamics of spiral arm formation and how that translates into star formation. Is that, you obviously didn't have time to cover that, but is that actually being thought about seriously by your team?
I'm not so sure about spiral arm formation itself, but we are studying the effect of morphology, galaxy morphology on the impact that it has on the cloud properties and so on. And also we are dividing the samples into barred and unbarred galaxies. I think that's all I can say for now. Okay, because there are, papers and so on that describe how stars form in connection with the spiral arms of bars. Yeah. And so like, how through the molecular clouds and so on. And so this ought to be the evidence. Yeah, so like we are also seeing number distributions of clouds before it passes the spiral arm, and then how it disperses as long as it travels away from the spiral arm. And there seems to be a decline of the number density, and we're still looking into it.
I was curious that, again, beautiful images and related to what Risa was saying earlier about the scale height, limiting the bubble size. Is there any, I see a lot of galaxy images that are face on spirals. Are there any ones that are edge on?
No,
And no.
no.
Okay. There's not a wide variety of inclination angles that we're looking at?
Only inclination less than 75 degrees. We try to focus on face-on galaxies.
Huh.
Because if it's edge on, there will be contamination like in the line of sight, and we don't want that for now.
Could be interesting. Thanks.
Fantastic. Let's thank Jaeyeon again. And welcome to KIPAC.